The graph of a function f shown above consists of a semicircle, a little one there, and 3 line segments, 1, 2, 3. Let g be the function given by g of x equals f of t. This is the graph of f of t dt from -3 to some random x. Part A. Find g of 0 and g prime of 0. Now, this is what we call a typical accumulation function. What makes accumulation functions so difficult is that you really have to know the concepts of derivatives and integrals very precisely in order for you to get these questions. They are, for the most part, quite easy to do if you know the concepts, and pretty much impossible for you to do if you don't know the concepts, and you're just going to have to leave them blank. So, if you know that this is an accumulation function, it might be a good idea to make a little legend or key to the side that really lets you understand what g of x means and what f of x or f of t means in this case, okay? Because if you look through all these questions, all the questions are in terms of g prime. We're talking about g, and g. However, the graph here gives us no information about g. It only gives us information about f. And the only connector between g and f is this statement here. And of course, this is a classic integral or area under the curve relationship. So let's take a moment to just pause and make a legend or key where we can describe what g and f really mean. So, for example, I know that g of x is equal to the integral from -3 to x of f of t dt. Okay? And we also know that we need information about g prime. And then, we might as well get information about g double prime because the first and second derivative are pretty important in most cases. All right, so if this is g, and I wish to know information about g prime, well, can't we really say that if I go from g to g prime, then I'm taking its derivative? If I take its derivative, then I'm really taking the derivative of this. I'm taking the derivative of the integral of f of t. Now, the derivative of an integral, on the side, if you derive d dx, is the symbol for derivative. If you derive an integral, what do you think you get? Okay, remember, derivatives and integrals are inverse functions, so they will pretty much undo each other. They will, in a sense, cancel each other out, and that's the simplest way to look at this. So if I take the derivative of an integral here, as we need to do for g prime, then they pretty much cancel out, and you could think of it as this x, and that x, the upper limit of the integral, plugging itself into this t, and you get just plain f of x. F of x is this graph that we have here. Okay, so we know for sure that g prime is equal to f of x. Okay, and then let's take it one step further because these questions might ask about g double prime. Okay, and just like what we did in this kind of first derivative here, we're going to just derive this one more time. And when we derive that, the derivative of f of x is, of course, f prime of x. Okay, and then this is my little legend or key that I will be using so that I can make sense of all these questions. Okay, and really this is all you need. I'm going to put this in a little cloud, and then we'll see if we can answer these questions which are all pretty much concept-based and not mathematically based in the next part. Okay? So, this cloud is taking some time here, huh? All right, so if I want to know about g of 0, well, what's really happening is I'm taking this function and I'm basically saying, well, what is g of 0? All you got to do then is you have the connector here. You want to know the integral from -3 to now x is 0 this time. And that's going to be of f of t dt still. Okay, remember, f of t dt is this function. So if I want to get the integral from -3 to 0 of f of t, well, you have to remember that this concept of the integral simply means the area underneath the curve. Okay, so all I got to do is find the area underneath the curve between 0 and -3. Now keep in mind, if I'm going from 0 to -3, oh, excuse me, sorry, I'm going from -3 to 0, that's the normal way it goes. We just have to find, through any means, the area underneath that curve. So, here we have -3 and 2. And then we're going to take it all the way to 0. And essentially, we are going to find this area here. Okay? Now, we don't have an equation. All we have is just our prior math skills. This can be interpreted as a trapezoid. But if you're too lazy to use the formula for a trapezoid, you can certainly distinguish this as a rectangle and a triangle. Why don't we take care of it that way? Okay, I spy a rectangle here. We have a rectangle that is 1 unit long, 3 units wide. Well, then this area has to be 3. 3 times 1. Okay, and then we have a triangle here, which is really just half of a rectangle, and that half of a rectangle may be right here. Okay, that's the same rectangle that we have down here. So this area must be 1.5. Okay, in other words, the area between -3 to 0 is going to be 3 plus 1.5 g of 0. Excuse me. G of 0 equals 4.5. Okay. All right, now we want to find what is g prime of 0. Okay, completely different question. Not going to be any way related to g of 0. So we're going to look at our little cloud. We're going to look at our little key. We mentioned earlier that g prime of 0 is indeed equal to f of x. And again, the only clues that we have of f of x is this is the graph of f of x. In other words, this line, this curve is f of x. And if I want to know g prime of 0, then really I just need to figure out what is f of 0. Okay, f of 0 can be interpreted from the graph. F of 0 is given right here. It is exactly going to be 1. Okay, so g of 0, g prime of 0 equals f of 0, and this equals 1. Okay, if I scan through part B, find all the values in the open interval -5 to 4, which is what we have here, at which g attains a relative maximum. Justify your answer. Okay, if I look at this question, the key word here, what stands out to me, is g attains a relative maximum. when you read relative maximum, you have to translate this into calculus. Relative maximum. What derivative or possibly function relates to relative maximum? Is it g of x? Is it g prime of x? Or is it g double prime of x? When we talk about relative maximum, then we're talking about its first derivative. Okay? The first derivative tells you about increasing, decreasing, maxes and mins. The second derivative tells you about concavity, concave up, concave down, or points of inflection. So if we're talking about g attaining a relative maximum, we need to look at g prime of x. Now, back in the world of derivatives, when you did the first derivative test, this is where you derive, you get f prime. You'd usually make a number line. Okay, and let's say, for instance, we have some sort of maximum happening at x equals 5. In order for this to truly be a maximum, what I like to see for the values of f prime is positive values, then hitting 0 for the tangent line, and then translating into negative values. In other words, the derivative or the tangent lines of my function will be positive slopes like this on f, and then negative slopes while hitting a 0 slope on the top, hence making this the maximum point, okay, a relative maximum point. So, if this is true using the first derivative test, and I know it gets confusing with the notation, I know I used f prime here because that's usually what we use. In this case, we're talking about g prime. G prime is f of x, it is this graph, and what we have to figure out on this graph is, when do I get, again, we're talking about g prime, which happens to equal f of x. When does f of x go from positive values, hit 0, and then turn negative? Where on this graph does that occur? Okay, and this graph, or this part, occurs right at negative 4. If we look at negative 4, let's take a moment to observe this point. Oh, excuse me. Not a negative 4, rather this goes negative positive, that's going to be a minimum. This is going to go exactly at positive 3. And let's examine why. We have a positive value of 1 here, okay? And then maybe we move down a little bit. We're still positive, 0.9, 0.5, 0.3. We hit 0. In other words, these are all positive values. We hit the value of 0, then we're negative 0.1, negative 0.5, negative 0.9, and then negative 1 when we hit 4. These are negative values. So I hope that you can see that on the graph of f, which represents g prime, we have positive values changing into a 0, changing into negative values, which proves that my original function of g must be increasing, 0 slope, and then decreasing here. Okay, so we are attaining a relative maximum on x equals positive 3. All right, let's look at part C. Find the absolute minimum value on g on the closed interval negative 5 to 4. Now, again, the key word here is minimum value, but don't forget that absolute minimum value is a little bit different from a relative minimum value. Remember, on a closed interval, if we want to know the absolute minimum point, or the absolute minimum value, it has to be the absolute lowest. It's not guaranteed that it is your relative minimum, so you must check. Okay? But in any case, if I want to know the minimum value, it's pretty much the same idea as part B. We're still looking at the first derivative. We're still looking at the derivative of g, which again is equal to the graph of f. And this is what I'd like to see on the graph. Let's say this happens at 2. Well, g prime must be negative, have negative values, cross through 0, and then have positive values for it to be a minimum, because negative values on g prime means that you are decreasing on g. Zero slope means that you have a zero slope, and then positive values on g prime mean that you are increasing, and this definitely forms a relative minimum here. So where does this occur on the graph? Well, there's only one place that I see this occurring, and let's see if you guys can figure it out. It's what I put originally. This is the location of a relative minimum. Again, it's very important for us to connect these two ideas. Let's see this happening here. We have negative values on f, which represents g prime. We have negative values such as negative 1, negative 0.9, negative 0.5, 0. Then we go to positive 0.1, positive 0.5, positive 1. Go from negative values, 0, up to positive values. Exactly what we're seeing on this number line here, exactly the shape of a relative minimum. Okay, but again, don't forget that this question says absolute. Absolute means I have to also check what's happening at negative 5 and what's happening at 4, because they could have the absolute minimum values. Okay, so we have to check negative 5, positive 4, and then our candidate here, which is at, negative 5, positive 4, and negative 4 is also a candidate. Okay, so you can simply check that. If you want the actual minimum value on g, then all you got to do is plug these numbers in to g and see which one gives you the smallest value. So really all I have to figure out, again, you got to check your endpoints. You got to find g of negative 5. You got to find g of negative 4, because that was our relative minimum. And then you got to find g of positive 4. Okay, g of negative 5. This takes us back to our original function, which is just the integral of the graph, which again means just the area underneath the curve of that graph. So we're going to take the area underneath the curve from negative 3 all the way to negative 5 of f of t dt. Okay, let's just set all these up real quick. Again, these are all g's, which is the integral of the graph. We start at negative 3, now we're going to negative 4 f of t dt. And then for the last one, negative 3 goes to positive 4 f of t dt. Okay, we have to figure out which one of these gives us the smallest value, and that will be the absolute minimum value. Okay, one thing that I do notice is that when I look at the first two areas, I'm starting at negative 3. I'm starting at this point here. And then I'm going to negative 5. Well, that is actually going to the left, or that's going backwards. Normally, we like to go from left to right. So you have to get the opposite area if you go in the opposite direction. So for negative 5 and negative 4, we are moving in the opposite direction. We're going to have to flip it and get the opposite area. And then for the last one, that's a kind of normal area underneath the curve. Well, let's be real logical here. I like to travel from -3 to -5, which means I'm traveling from this moment all the way to this moment. Now, what do you notice about these two triangles? One triangle is above the x-axis, making it positive, and the other triangle is below the x-axis, making it negative. If I were to add up these two areas, then they will simply cancel themselves out, because this is called the signed area, where you could have negative areas. So in other words, this triangle will cancel out with this triangle, which pretty much means that g of -5 is just going to make nothing, 0. Okay? All right. Now we want to just travel from -3 to -4. Well, that's just the area of this triangle, but as I mentioned before, I am moving from right to left, which means that this positive area of this triangle is all of a sudden going to turn negative of this purple area. Okay, this is a triangle with a base of 1 and a height of 2. So then you're going to take half of that rectangle, which is 2 times 1. Half of 2 is going to give you exactly 1. But instead of saying this is positive 1, imagine it being below the x-axis. This is going to be represented as -1. Okay, so let's pause here. Who is the absolute minimum so far? Well, it looks like at -4, its value is much lower than when we have a -5. So -4 is the winner so far. Let's check what happens at +4. This is the area from -3 all the way to +4. Now, I could go ahead and take the area of this, but what I notice is, again, here I'm traveling normally from left to right. That means that everything above the x-axis is going to be positive area, everything below is going to be negative area. And as far as I can see, from here to here, the positive territory is much larger than the negative territory. In fact, this little triangle is the only negative part, which means that this overall will give you a positive answer. Okay, so definitely on the AP test, you want to still find this area, get it precisely, just to prove to the reader that this area is smaller. But as far as I can do with my eye test or my mind test, there's no way that the area from -3 to 4 is going to be smaller than this -1. Okay, and finally for the last section here, find all the values of x on the open interval -5 to 4 at which the graph of g has a point of inflection. Again, let's think about the key terms here. We're talking about g has a point of inflection. All right, don't forget about our key, our little key that we made to help us with this problem. If we're talking about point of inflection, are we talking about g of x, g prime of x, or g double prime of x? We are definitely talking about g double prime of x, where we're talking about concavity and changes in concavity, which represent your point of inflection. Remember, we do not have any information about g here. We only have information about f. G double prime, we said earlier, is congruent, or is the same thing as saying f prime of x. Well, we don't have any graph of f prime of x, but we could get information about f prime of x by looking at the graph of f. You have to remember what the derivative means when you just have a graph. Remember, first semester, derivatives. All derivatives mean on a graph is the T word, tangent line. We're talking about tangent lines here. So, similar to what you did in the first semester, we can kind of make an informal second derivative test where we have a little number line and get the derivative of these graphs, of these lines. Okay, now keep in mind, remember, when you take the derivative, you always want to kind of frame the derivative by figuring out where you're going to have maximums and minimums, because those will translate into the zeros on f double prime. Let's see, let's not label this f double prime. We'll call this g double prime just because it's so confusing, which is equal to f prime. And that is what I want to take the second derivative test of. Okay, so as far as I can see, the maxes and mins, we can confirm it once we begin. I think I see a maximum here. Maybe that will translate into a g double prime being 0. I see a minimum here. Maybe that'll translate into g double prime being 0. And we also have a cusp, a pointed curve here. But remember, those can still be a max or min. All right. So all I care about, again, when I derive f for f prime is the derivative, the tangent lines. So let's get those tangent lines. If I just kind of look at this interval, all the tangent lines here on this sort of flat line are all pointing up, and they're all the same. These all have a positive tangent line. So at least from -5 all the way to -3, I would categorize these as positive tangent lines. Okay. If I check from -3 to 0, we're going in this direction, decreasing. This will give you negative tangent lines. So this is negative. In fact, if I take tangent lines here on this curve, these tangent lines are also going to be negative. And then we're going to stop here, and then we're going to change, it seems like. So from -3 to 1, it seems, all of these are negative values of g double prime. Okay, and then when we go to 1 to 2, we see that we have positive tangent lines, positive values of g double prime. And then from 2 all the way to the end of the interval at 4, these are all headed downward. So we're decreasing. That means we have negative tangent lines. Okay, excuse me for that. The video keeps shutting off. And you see these red circles here. Let's see why exactly I circled them, why these arrows are pointing in the directions that they're pointing. Let's have a look. At -3, at +1, at +2, something interesting is happening. We have a relative maximum here, relative minimum here, and a relative maximum here. And notice how when you take the tangent line or derive these maxes and mins, they end up being points of reflections on g double prime, on the second derivative. Okay, so basically we have points of reflection at -3, +1, and 2, because we know for sure that we are changing concavity between those three numbers.